Imagine walking into a field before sunrise. The air smells of fresh soil. The morning mist hangs low over endless rows of crops, and suddenly hundreds of machines wake up at the same time. Tractors steer themselves within a few centimeters of perfect accuracy. Drones skin thousands of plants every minute, and robots decide exactly where every drop of fertilizer belongs. But here's what nobody tells you. Inside every one of those intelligent machines hides one of the most advanced manufacturing stories on Earth. Today, we're going far beyond the farm and into the factories where steel, silicon, satellites, artificial intelligence, and human ingenuity come together to build the future of agriculture.
Think about this. One modern autonomous tractor can process more than 200 hectares during a planting season while collecting millions of pieces of data about soil moisture, engine performance, wheel slip, fuel consumption, and crop conditions. Every second, dozens of sensors communicate with satellites orbiting hundreds of kilometers above Earth. What happens next surprised even experienced engineers, because the real magic doesn't happen in the field. It begins thousands of kilometers away inside mines, steel mills, semiconductor factories, and electronics laboratories spread across the globe. Most people see a green tractor, a drone, or a robotic harvester and think it's just another piece of farm equipment. In reality, it contains thousands of precision-engineered components, some manufactured to tolerances thinner than a human hair. The steel frame must survive decades of vibration, mud, dust, blazing summer heat, and freezing winter mornings. Meanwhile, its electronic brain constantly makes decisions faster than any driver ever could. By the end of this journey, you'll never look at farming equipment the same way again. Every smart farming machine begins deep beneath the Earth's surface. High-strength iron ore comes primarily from enormous open-pit mines in Western Australia and Brazil, where giant haul trucks weighing more than 600 metric tons carry or containing around 60 to 67% iron. The ore travels hundreds of kilometers by rail before reaching coastal ports, then crosses oceans aboard bulk carriers capable of transporting more than 200,000 metric tons in a single voyage. Long before a tractor touches a field, its journey has already circled half the planet. Inside steel plants, those reddish rocks transform into the skeleton of tomorrow's agricultural machines. Blast furnaces reach temperatures close to 1,500 degrees Celsius, or nearly 2,730 degrees Fahrenheit, as purified iron combines with carefully controlled amounts of carbon, manganese, chromium, and molybdenum. These alloying elements create steel that stays incredibly strong while resisting corrosion, fatigue, and constant mechanical stress. Every kilogram of steel must perform flawlessly after years of bouncing across rough farmland.
But steel tells only part of the story. Lightweight aluminum comes from bauxite mined in Australia, Guinea, China, and Brazil. After refining, the metal becomes transmission housings, engine parts, drone airframes, and precision brackets that reduce weight without sacrificing strength. Every kilogram saved means lower fuel consumption, higher efficiency, and less soil compaction, something farmers care about far more than most people realize.
Now imagine shrinking your attention from giant steel beams to something almost invisible. Deep inside every smart farming machine lies a network of microchips built from ultra-pure silicon. The silicon starts as quartz mined in countries including the United States, Brazil, China, and Norway. Engineers purify it to more than 99.9999999% before turning it into mirror-like wafers that eventually become processors capable of analyzing millions of farming decisions every second. Those tiny processors depend on metals that travel even farther. Copper from Chile and Peru carries electrical signals through kilometers of wiring. Gold protects delicate electrical contacts from corrosion. Rare earth elements such as neodymium help build powerful electric motors and precision sensors, while lithium, nickel, and cobalt power autonomous drones and battery electric equipment. Most people never think about this, but a single intelligent farming system may rely on materials extracted from more than 20 different countries. Then comes the invisible supply chain. Shipping containers leave ports in Asia, Europe, North America, and South America carrying engines, bearings, hydraulic pumps, cameras, radar modules, GPS antennas, electronic controllers, and precision fasteners. Some components travel more than 15,000 kilometers before reaching the same assembly plant. Engineers schedule every shipment almost to the hour because one missing sensor can stop an entire production line worth millions of dollars. There's another side to this incredible story. Mining, steelmaking, and transportation consume enormous amounts of energy and produce significant carbon emissions. Manufacturers now recycle large percentages of structural steel and aluminum, use electric arc furnaces powered by renewable electricity, and redesign machines to reduce fuel consumption throughout their working lives. The goal isn't simply building smarter equipment. It's building equipment that helps produce more food while using fewer resources than ever before. So now we know where the ingredients come from. Mountains become metal, sand becomes artificial intelligence, and minerals from across the globe converge inside one extraordinary machine. But here's the question that changes everything. How do thousands of raw components become a self-driving tractor accurate enough to plant seeds within just a few centimeters, hour after hour, day after day? That's where the factory doors finally open. The moment those factory doors slide open, the atmosphere changes completely. You hear the deep hum of overhead cranes, the sharp crackle of robotic welding arcs, and the steady rhythm of thousands of machines working together with almost unbelievable precision. Every smart tractor, sprayer, combine harvester, and autonomous robot follows an exact production sequence that engineers have refined over decades. Miss a single step, even by a few millimeters, and the entire machine could fail years later in the middle of harvest. Everything begins with massive steel plates arriving from the rolling mill. Computer-controlled fiber lasers, some exceeding 20 kilowatts of power, slice through high-strength steel with cutting tolerances as tight as plus or minus 0.1 millimeter. Nitrogen or oxygen-assist gas blows molten metal away from the cut, while the laser head races across the sheet at speeds approaching 25 meters per minute. The air smells faintly of hot steel, and bright sparks scatter like miniature fireworks across the factory floor. Next comes robotic forming. Hydraulic press brakes generate forces exceeding 300 tons, folding heavy steel components into perfectly shaped chassis rails and structural supports. Sophisticated sensors constantly measure each bend and automatically compensate for tiny changes in material thickness. What looks like brute force actually depends on astonishing mathematical accuracy measured in fractions of a degree. Next comes robotic forming. Hydraulic press brakes generate forces exceeding 300 tons, folding heavy steel components into perfectly shaped chassis rails and structural supports. Sophisticated sensors constantly measure each bend and automatically compensate for tiny changes in material thickness. What looks like brute force actually depends on astonishing mathematical accuracy measured in fractions of a degree. Blue arc flashes almost faster than your eyes can follow, while ventilation systems pull away the rising smoke. The welded chassis then enters a heat treatment furnace where temperatures typically range from 540 to 620 degrees Celsius, or 1004 to 1148 degrees Fahrenheit, depending on the steel grade. During several hours of carefully controlled heating and cooling, internal stresses relax without weakening the structure. Engineers know that this invisible step dramatically increases fatigue life after years of rough field work. You can't see the improvement, but you'll certainly notice it after 10,000 hours of operation. After cooling, automated blasting machines fire tiny steel shot at incredible speed, stripping away oxidation while creating the perfect surface for paint adhesion. Powerful extraction systems capture dust as robotic sprayers apply corrosion-resistant primer followed by multiple protective coatings. The painted frames bake inside curing ovens at around 180 degrees Celsius, or 356 degrees Fahrenheit, until the finish becomes incredibly durable. That glossy green, red, or yellow color isn't just for appearance. It protects the machine from years of rain, fertilizer, chemicals, and ultraviolet sunlight. While the frame moves through finishing, another production hall builds the heart of the machine. Engine blocks begin as precision castings before CNC machining centers remove tiny amounts of metal using carbide cutting tools spinning between 3,000 and 10,000 revolutions per minute. Cooling fluid continuously washes away metal chips while the machines hold dimensional accuracy within just a few microns. The steady sound of high-speed cutting mixes with a scent of warm lubricant and freshly machined steel. Nearby, hydraulic systems come together. Precision ground pistons slide into polished cylinders while automated stations install seals capable of withstanding pressures exceeding 250 bar, or more than 3,600 psi. Every completed hydraulic circuit undergoes pressure testing with specialized oil before approval. Even a microscopic leak could reduce lifting power or steering accuracy in the field, so inspectors refuse to compromise. Finally, everything converges on the main assembly line. Engines lower into painted chassis with overhead cranes while robotic systems install transmissions, axles, hydraulic lines, electrical harnesses, fuel tanks, GPS antennas, LiDAR sensors, radar units, cameras, and climate-controlled operator cabins. Some assembly stations allow less than 12 minutes before the conveyor advances to the next position. Thousands of individual parts now move as one machine, and for the first time, it begins to resemble the intelligent equipment that will soon transform fields around the world. But assembling the machine is only half the challenge. Engineers still have to prove it can survive years of brutal dust storms, freezing winters, scorching summer heat, relentless vibration, and non-stop operation without losing even a fraction of its precision. The next stage pushes every sensor, every bolt, every weld, and every computer to its absolute limit. And some machines never make it past the tests. The production line may have ended, but the real challenge is only beginning. Every smart farming machine must now prove that it deserves to leave the factory. Engineers don't trust appearances. They trust data, measurements, and relentless testing. What happens next surprised even experienced farmers, because some brand new machines worth hundreds of thousands of dollars never make it past this stage. The production line may have ended, but the real challenge is only beginning. Every smart farming machine must now prove that it deserves to leave the factory. Engineers don't trust appearances. They trust data, measurements, and relentless testing. What happens next surprised even experienced farmers, because some brand new machines worth hundreds of thousands of dollars never make it past this stage. The first inspection begins with laser metrology. Robotic laser scanners sweep across every surface, creating millions of measurement points in just a few minutes. The completed digital model compares instantly with the original CAD design, revealing dimensional differences as small as plus or minus 0.05 millimeters. If even one mounting bracket falls outside tolerance, the machine leaves the production line for immediate correction. Next comes artificial intelligence. High-resolution vision systems photograph every weld, bolt, hydraulic fitting, wiring harness, and painted surface from dozens of different angles. AI software compares each image against millions of reference examples, detecting scratches, paint defects, missing fasteners, cracked welds, and damaged electrical connectors within seconds. The rejection rate often stays below 2%. But those few machines receive immediate repairs before testing continues. Then engineers test the nervous system of the machine. Thousands of electronic signals race through kilometers of wiring as computers verify every sensor, camera, GPS receiver, radar module, LiDAR scanner, steering motor, and hydraulic valve. A single autonomous tractor may contain more than 100 electronic control units communicating across multiple high-speed networks. If one signal arrives even milliseconds late, engineers investigate before approving the machine. Now the machines face conditions far worse than most farms will ever experience. Inside environmental chambers, temperatures swing from minus 40 degrees Celsius, or minus 40 degrees Fahrenheit, to nearly 85 degrees Celsius, or 185 degrees Fahrenheit. Powerful hydraulic shakers recreate years of vibration in only a few days, while fine dust fills the air to challenge every seal, bearing, and cooling system. The constant rumble echoes through the building like distant thunder. Hydraulic performance testing pushes the equipment even harder. Pumps generate pressures above 300 bar, or roughly 4,350 psi, while robotic test rigs repeatedly raise and lower heavy loads for thousands of continuous cycles. Sensitive instruments monitor pressure fluctuations, fluid temperatures, flow rates, and microscopic leaks. Every successful cycle increases confidence that the machine will perform flawlessly during the busiest days of harvest. After that comes the proving ground. Test drivers and autonomous software guide the machines across steep hills, deep mud, loose gravel, flooded tracks, and rough terrain designed to accelerate years of wear into just a few weeks. Radar watches for obstacles while GPS corrections keep steering accuracy within approximately 2.5 centimeters under ideal RTK conditions. Watching a driverless tractor navigate obstacles with almost perfect precision feels less like farming and more like science fiction. But here's where human skill still beats machines. Veteran inspectors run their hands across painted panels, listen to engine vibrations, and notice tiny sounds that computers sometimes overlook. An experienced technician can hear an unusual bearing tone or feel a slight hydraulic pulse before any sensor reports a problem. Decades of craftsmanship still matter, proving that technology works best when it amplifies human expertise instead of replacing it. Only after passing every inspection can the machine earn international quality certifications and receive final software calibration. Engineers upload the latest operating algorithms, verify satellite communication, and record every measurement in a permanent digital history file. From that moment forward, the tractor carries a manufacturing fingerprint that technicians can trace years into the future. Every bolt, every sensor, and every software version becomes part of its story. At last, the factory doors open once again. Perfectly finished machines roll onto transport trucks bound for farms across every continent, ready to plant, spray, harvest, and feed millions of people. Yet one incredible mystery still remains. How many of these remarkable machines does the world build every year? Which countries dominate the industry? And what astonishing changes are about to reshape farming forever? The numbers are far bigger than almost anyone imagines. Machinery industry worth well over $200 billion, and demand continues to grow as the world race. Now that you've seen how these extraordinary machines are born, let's zoom out and look at the bigger picture. Every year, manufacturers around the world build well over 2 million tractors, along with hundreds of thousands of combines, sprayers, seeders, balers, autonomous robots, and precision farming systems. Together, they form a global agricultural S to feed a population expected to approach 10 billion people. Think about this. Without these machines, modern agriculture simply couldn't keep pace.
Behind every machine stands an enormous workforce. Millions of people contribute to this industry, including miners, steelworkers, foundry operators, machinists, electronic specialists, software engineers, robotic technicians, logistics experts, quality inspectors, and field service mechanics. Most people never think about this, but one autonomous tractor represents the combined knowledge of thousands of skilled workers spread across dozens of countries. It truly is one of humanity's largest collaborative engineering achievements.
The transformation over the past 50 years has been astonishing. In the 1970s, most tractors relied almost entirely on mechanical controls, paper manuals, and operator experience. Today, satellite navigation, cloud computing, artificial intelligence, machine vision, and real-time analytics guide machines with astonishing precision. What once required several operators can now happen automatically, while every square meter of land generates valuable digital information. And this is where it gets truly extraordinary. Over the next decade, autonomous machines will work together in coordinated fleets, electric tractors will become more common, and artificial intelligence will analyze crops plant by plant instead of field by field. Swarms of drones will monitor disease before the human eye can detect it, while robotic harvesters pick fruit with remarkable gentleness. The future of farming won't simply replace hard work. It will multiply the skills of every farmer on Earth. Here's our first did you know? A single modern combine harvester can harvest enough grain in one day to produce bread for tens of thousands of people. Here's another. Precision agriculture can reduce fertilizer and pesticide use in many applications by targeting only the areas that actually need treatment, improving efficiency while reducing waste. And one more. Some autonomous farming systems can steer with repeatable accuracy of just a few centimeters, season after season, using advanced satellite correction signals. From iron ore buried beneath ancient mountains to intelligent machines navigating fields with satellite precision, you've followed one of the most remarkable manufacturing journeys on Earth. Every weld, every circuit board, every sensor, and every software update exists for one purpose: to help farmers grow more food with greater efficiency, accuracy, and sustainability than ever before. The next time you see a smart tractor crossing a field at sunrise, you'll know you're looking at far more than a machine. You're looking at decades of engineering, millions of hours of human innovation, and a global manufacturing network working together to feed the world. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.